All right, guys, moving into part 5 of this course, and there's only 7 parts, so we're moving right along. And part 5 is our first chapter on inference, and I've been mentioning things about inference all along. We've been laying the foundation for inference. In fact, this 17 is our last foundation chapter. We're not going to quite yet do inference until chapter 18, but we've been laying the groundwork to do inference. And inference, and I know this isn't very clear, but inference is when we take information from a sample and infer or project that information onto a population. Sampling is when we take our population and draw a sample, but when we take the sample, collect data from the sample, and then use that data to infer on the population, that is what inference is. This unit, part 5, is all about inference for the proportion. So we're only going to be talking about categorical data. Categorical data. For proportions, that's categorical data. Remember, proportions, same thing as percentages. If we were doing numerical data, we would be doing inference for the mean, not the proportion. Okay, so make sure you know that you summarize categorical data with a proportion or a percentage, and quantitative data with a mean or an average. 17 actually does proportion and mean, and then the rest of the unit is just proportions. I've decided to only focus on proportions for 17, and when we get to chapters or part 6, I'll come back and do 17b, the second half of 17. All right, the central limit theorem is one of our primary theorems that we use in this course. It's the foundation for inference. We have a All right, so we'll be looking at the central limit theorem for proportions. We just finished off last chapter talking about the binomial model, where we look at the number of successes in a set number of trials. But what if instead we examined the proportion, which is just the same word for percent, of successes instead of the number of? And that's what we're going to be moving into. So we're really just kind of using the binomial model like we've been learning, except turning it into a percent instead of a proportion, instead of a number of. So think back to Randy. If Randy shot 20 in out of 30, binomial, we were looking at the number 20. But when we turn it into proportion, we just divide it by n, divide by 30, and we look at the proportion. He made 2/3 of his shot. Imagine if we took every sample of a particular size and then made a histogram of each sample's proportion of success. We wonder what that histogram might look like. We would expect that this histogram of sample proportions to be centered at the true proportion P in the population. So whatever the true proportion is in the population, we would expect this histogram of sample proportions to be centered at that true population proportion, because most of our samples should be near it. So that's like the average. Now, what would you think the shape of this histogram would be? The way we decided this is originally they did a whole bunch of simulations. And I'm going to actually do one with you. We can simulate a bunch of random samples that we don't really draw in real life, because that would take a really long time. But if we simulate it with a computer, then we can start looking at the shape of this histogram. And you've actually already been doing this. When we did our DICE activities and our Randy activities, we were simulating drawing random samples. And it turns out that this histogram is symmetric, unimodal, and centered at P. P is the population proportion. More specifically, it's an amazing and fortunate fact that a normal model is just the right one for the histogram of sample proportions. So no shocker there. We already knew we could use the normal model for binomial if the conditions were met. And we have the same conditions for this, and we'll talk about those in a minute. Modeling how sample proportions vary from sample to sample is one of the most powerful ideas we'll see in this course. This is what the central limit theorem is all about. It's what we think those samples proportions will look like. A sampling distribution model for how sample proportions vary from sample to sample. Keep thinking about what that means. allows us to quantify that variation. And being able to quantify variation with, say, a standard deviation is how I know if a sample is, or if a sample's proportion is unusual or not. That's how I can decide, was that supposed to happen or was that kind of strange? To use a normal model, we need to specify its mean and its standard deviation. So we'll call mu, the mean, to be centered at P. But what standard deviation? Well, when working with proportions, knowing the mean automatically tells us the standard deviation. And the formula for this is P square root of PQ over N. And this is on your formula sheet. Locate it on the bottom right. It's also on the back side. This formula comes directly from the binomial formula, square root of N times P times Q. If we divided that by N, it would work out to be this. And so our model is normal, centered at P with a standard deviation of PQ over N. And here is a picture of that model, centered at P with our 3 standard deviations in either direction with a standard deviation of square root of PQ over N.